Hi, in this video we're going to look at these two sets of vectors and we're going to try to show, using the definition, which set is linearly independent and which set is not. So one thing you might notice about these two sets of vectors is that they are almost exactly the same vectors. The only thing that's different is that very last entry in the last vector is a little bit different. So one thing I want to point out is that it's very difficult to tell just from glancing at a set of vectors, particularly if there are very many of them in the set, more than two, really. It's very difficult to tell just by glancing at the set whether the set is linearly independent or not. And I've set these up so that one of these sets is linearly independent and one is not. But in general, if you're asked to show whether a set is linearly independent or not, you would do the problem the exact same way we're going to do it here. All right, so if you've had some linear algebra, you might know some theorems that you could also use to accomplish this task, but we're going to just use the definition of linear independence as a way to determine which of these sets is linearly independent or not. So remembering that the definition of linear independence is about taking a linear combination of the objects in the set and setting that equal to the zero vector. So in this case, the zero matrix that is 3 by 1 with all zero entries. All right, so I'm just going to write down linear combination of these and set it equal to the zero vector. You don't always have to write this step out unless you're really wanting to demonstrate that you are actually using the definition of linear independence. Okay, so I've just written down a generic linear combination of those three vectors in the set and set that equal to the zero vector. That's the definition of linear independence, is about what kinds of scalars make this equation true. Always, it should be pretty obvious that when the scalars are zero, this equation will be true. That's part of what happens in that definition. A linear combination, when the scalars are all zero, will always give you the zero vector in your space. But the question is, are there more solutions than that? So in essence, this is the definition of linear independence, the start of it. To answer the question, I need to determine if there is only one set of constants that make this equation true, or if there are more sets of constants that make this equation true. So one way to accomplish that is just by solving the system of equations that you're going to get when you go ahead and do this scalar multiplication and vector addition. So I'm going to skip a step here just for some space. I might, if I were going to write out every step, go ahead and do the scalar multiplication and matrix addition. So I would have a vector, a 3 by 1 vector, equals the zero vector. And then I would write a little system of equations based on those entries. I'm just going to write the system of equations here based on the entries. So for the first entries, I would have C1 minus C2 plus 0 times C3, so no term there, equals 0. And then for the second one, C1 plus 3 times C2 plus 2 times C3 equals 0. And then for the third entry, 2C1 plus 4C2 minus 3 times C3 equals 0. So here I have a system of equations with unknowns C1, C2, C3. So I need to solve this system either by hand. You could use elimination or substitution or whatever method you want to solve by hand, or you could put that into a calculator and do a matrix and do a reduced row echelon form of the matrix and use that to help you solve this system. So you want to solve this system. I already did that, so you should maybe pause the video and do that and see if you get the same thing I'm going to get. But when you solve that system, you're going to get as a solution that C1 is equal to 0 and C2 is equal to 0 and C3 is equal to 0 as the only solution. Okay, so based on that definition of linear independence, a set is linearly independent if the only linear combination that gives the zero vector is when all of the scalars are 0. So this work here using the definition of linear independence tells us that this set is linearly independent. All right, so notice this other set is almost exactly the same. I just changed that last entry and the third vector there. So I told you at the beginning of this video that one of these sets is linearly independent and the other one is not, but you wouldn't necessarily know that if somebody hadn't told you that just by looking at it. But if I'm going to use the definition of linear independence to determine whether this set is linearly independent or not, my steps are going to be basically the same. So I'm going to take linear combination of my vectors equal to the 0 vector, write down a system of equations, and use whatever method is appropriate to help you solve that system of equations. And again, if you have had a lot of linear algebra, you may know some shortcuts here that could help you get to this result quicker. And that's fine with me in my classes, but depending on your purpose here, if you're wanting to demonstrate the definition of linear independence, for example, maybe you just go through and do what the definition is about. So you're going to solve this system. I used a reduced row echelon form of a matrix. So I put in an augmented matrix using the coefficients of this system of equations into a calculator or computer. And I did a reduced row echelon form of that matrix. I'm going to just go ahead and write down the reduced row echelon form of that matrix here. So I got 1, 0, 0.5. And then this last column obviously will just stay zeros. And 0, 1, 0.5, 0, and then the bottom row was all zeros. All right, so noticing here that I don't have a pivot in this third column, right? I have pivots here and here, but I don't have a pivot in that third column, which would mean that C3 is a free variable. And the key part here is that that means that this system has infinitely many solutions, right? Since this column does not have a pivot, C3 is a free variable. So this system has infinitely many solutions. Now I could write down what the solutions are. If I needed that for some reason. But if we're really just talking about linear independence or not, the key here is that the linear combination where the scalars are all 0 is not the only linear combination that makes this linear combination equal to the 0 vector. So that means I have infinitely many solutions, so that means that this set is not linearly independent. Or you could say that the set is linearly dependent. That's another way to say that. I tend not to say that with students that haven't had a lot of linear algebra, just because there's some double negatives and a lot of vocabulary there. Remembering that linear independence is generally what you're after. You usually would like to have a set that is linearly independent, at least for our purposes in this class, so that we can get a basis for whatever vector space we are looking at. All right, we'll look at some more examples in some other videos related to basis, but you should do some more practice about linear independence before you practice those next few things before we get to basis.